We want to find the peak element in an array. The idea is take any element. If it is bigger than all of its neighbors, then it is a peak element. So much like a mountain, it's the highest point in some localized part of that mountain. So if we have an array and we have an example 1, 1, 2, 3, 1, the peak would be 3 since 3 is bigger than both of its neighbors 2 and 1. There are some edge cases that we'll go over, which is if the value is bigger than its neighbors, then it's the leftmost value or the rightmost value, then that also counts as a peak value as well. Now, there are several ways to solve this problem, and one of them is by brute force, iterating through the array and solving it in linear time to say, is this value bigger than its neighbors, right? But there is a bit more of an efficient way to do this, and that's with binary search, okay? And as I've mentioned in other videos, it's definitely an algorithm that you want to keep in your back pocket for when you want to search for values. So first we start with 2 pointers saying low and high. Low is 0 and high is len of nums minus 1. And then we say if high is 0, return 0, right? That's the index of the value. If it's, if there's only one value in the array, right? Then it must be the peak. And then we have if high is 1, that means there's 2 values in the array, len of the array minus 1. And now we have two cases in there where we say if nums of 0 is greater than nums of 1, nums of 0 is greater than nums of 1, return 0. And if that doesn't pass, just return 1, because then that would make the other one have to be bigger than the other, 0, right? So there are a few more things that we have to deduce, and that is if we say if nums 0 is greater than nums 1, right, return 0. And then also if nums negative 1 is greater than nums negative 2, right, negative 2, return high, which is length of the nums minus 1. That's the index of the value that is greater than its neighbors, right, in this case. The rightmost value is greater than the second to rightmost value, which makes it a peak. Or if the leftmost value is greater than the second to leftmost value, then that makes it a peak as well. And then, of course, we have one more case, and that is if high equals 2, right? Now, if high equals 2, then that means we have an array of 3, right? We have an array of length 3. So then we say if nums of 0 is less than nums of 1, and that is greater than nums of 2, return 1, right? This is an edge case where we have just three values. After all of these edge cases, actually, we have just a general case, right? And this is where we come up with a very optimal solution, which is binary search. We say while low is less than or equal to high, mid equals low plus high divided by 2, right? Floor division. If nums of mid minus 1, is less than nums of mid, and that is greater than nums of mid plus 1, return mid. Okay, and then there's the other case where if nums of mid minus 1 is greater than or equal to nums of mid, and that is greater than or equal to nums of mid plus 1, high equals mid minus 1. Okay, else low equals mid plus 1. There's a lot to ingest here, so let's pause a second and review this. So this operates exactly like the binary search algorithm to find a value in a sorted array. Except in this case, we're looking for something kind of in the same manner, but not exactly. We're looking for a pattern, and based on that pattern, we update our index. And we say ultimately, if we find the peak, then we found the index where that peak exists, and we are good to go, return mid. That's the index where there's a peak. If we find that there is a non-increasing pattern for 3 elements, then we have to reduce our high index. We have to reduce our high index, right? Otherwise, low equals mid plus 1. Do the opposite. We run. Accepted, submit. Outstanding.